Hi, my name is Keyuan Lu. I'm a second-year graduate student from CIAC department at UF. Now I will do my final presentation of the course Wireless Communication. My project is about the evaluation of DSSS modulation under different channels. Here is the outline of my presentation. Firstly, I'd like to introduce what is DSSS. The full name of DSSS is Direct Sequence Spread Spectrum. Now, digital communication is very popular. It has strong anti-interference ability, especially after the digital signal is regenerated through the relay. It can eliminate the accumulation of noise. The digital signal is coded by error control to improve the reliability of communication. From the figure 1, you can see the spread spectrum model in digital communication system. In spread spectrum communication, we first encode the spectrum of the information to be transmitted to enlarge it many times. Send it to the channel for transmission, and then restore the information at the receiving end. Since the signal actually transmitted in the channel is expanded many times over the original signal spectrum, we call this technology spread spectrum communication. Since spread spectrum communication uses pseudo-random sequence for spread spectrum modulation and transmission, and signal reception needs to use the same pseudo-random sequence for related dispersing to recover the signal. This provides a basis for frequency division multiplexing and multiple access communication. Make full use of the autocorrelation and cross-correlation characteristics of pseudo-random sequence of different code types, and assign different pseudo-random sequence to different users to distinguish the signal of different users. Many users only need to use their own pseudo-random sequences, so people can use the same frequency to communicate without interfering with each other. And so it has advantages of realizing frequency division multiplexing and making full use of the crowded spectrum. As for DSSS, it has been widely used in military communications and confidential industries, and now even popularized in some high-end civilian products such as signal-based stations, wireless TVs, cellular phones. And about its features, DSSS phase modulates a sine wave pseudo-randomly with a continuous string of pseudo-noise code singles called chips, each of which has a much shorter duration than the information bit, and it uses a signal structure in which the sequence of chips produced by the transmitter is already known by the receiver. Now I'd like to introduce my DSSS system model. I considered using the DSSS system, which is used in BPSK modulation. The chip waveform matched the filter can be seen as an integral planar. In the transmitted end, I multiply the data being transmitted by a noise signal. The noise signal is a pseudo-random sequence of 1 and -1 values at a frequency much higher than that of the original signal. And as for the dispersing, I extract the original signal at receiver by using some basic logic operations on the received noise signal. You can see the operations in my slide. And now let me run the code of my project. I use MATLAB to do the simulation. So now here you can see my code can run successfully and make a simulation. In my project, End-to-end simulation of DSSS modulation started with generation of message signal at transmitter. I generated 8 bits message signal for better understanding of given figures below. Each bit has 0.1 second bit duration. Then I generated pseudo-random code that has 4 times higher frequency than message signal. This means that each message bit coded by 4 randomly generated bits at DSSS signal. To represent binary data, I used the num-return to 0 line code schema because I chose BPSK modulation to transmit my signal. BPSK modulation has 180-degree phase shift between carriers of binary zeros and ones. So binary binary 1 represented as 1 while binary 0 represented as -1. I obtained a DSSS signal with multiplying message signal and pseudo-random code. The receiver must be aware of this pseudo-random code, otherwise it can get transmitted message signal. And transmitted signal appears as a noise at receiver. In figure 1, it shows generated 8 bits message signal, pseudo-random code and modulated DSSS signal. And here is figure 2. Figure 2 shows the frequency spectrum of 8 bits message signal, pseudo-random code and modulated DSSS signal. And here is the figure 3. The result of decision device is shown here in figure 3. After I obtained the message signal at receiver with 0 error rate, I first tested DSSS modulation with additive white Gaussian noise, and results are obtained in terms of bit error rate. In short, it's BER. And BER is nothing but a ratio of numbers of error bits and the total number of bits transmitted during a specific period. While SNR value decreases, we checked the BER and analyzed. I expected to get good BER because DSSS modulation is known for its higher resistance to noise. I repeated each calculation 1,000 times and got a average value. As a result, I obtained a Monte Carlo analysis of BER with different SNR values. So here you can see 3 figures under different channels. So here in figure 1, this figure shows BER versus SNR plot while message signal has length of 100 bits. In Rayleigh fading channel model, there are one or more major reflected paths from transmitter to receiver. BER versus SNR plot of DSSS is given below, while signal is transmitted through Rayleigh fading channel. And here, the Rayleigh fading channel model is similar to Rayleigh, except it has direct line of sight paths in addition. Lastly, I would like to make a conclusion of my project. So in this project, I worked on end-to-end simulation of DSSS modulation. I used the message signal modulated by BPSK modulation technique. First, I assumed that I transmitted and received the signal without any channel effect. I demodulated received signals and obtained the message signal. At the last step, I analyzed the BER versus SNR plots by considering different situations, which are additive white Gaussian noise, Rayleigh fading channel, and Rayleigh fading channel effects respectively. I repeated entire process 1,000 times to draw Monte Carlo simulation distribution plots, while I increased the number of pseudo-random code. I obtained better BER results, and on the other hand, my modulation has higher resistance against the additive white Gaussian noise and lower resistance against the Rayleigh fading channel compared to others as expected. So here, above all, is everything of my project. Thank you.